Hi, everyone. I want to talk about water potential and share with you how I present it to my students and how you might want to introduce the topic. Probably the most important thing to remember, and I tell this to my kids, is that they probably already understand how water potential works, and we're just slapping some fancy names and equations on it. And here's what I mean. So, when I start talking about water potential with my students, I start by reviewing what I hope they had learned in ninth grade biology. And those are the terms hypertonic, hypotonic, and isotonic. Hypertonic means there's more solute concentration. But if there's more solute, that means a hypertonic solution has less water, right? Hypotonic means that there's a lower solute concentration, which means a hypotonic solution is going to have more water. And an isotonic solution has the same concentration of solute, so it's going to have the same amount of water. So most kids hopefully will at least be exposed to these terms in ninth grade bio. And it's great if they know this, but there's a problem with these terms. And the problem with these terms is this is that all three of these terms are relative terms. My cup of coffee might be hypotonic to your cup of coffee if you put more sugar in your coffee than I do. Or my cup of coffee might be hypertonic to a glass of water. So do you see what the problem is? Hypertonic, hypotonic, isotonic? They're good terms, but they're relative. So what we do with water potential is a calculation that allows you to assign a numerical value for water. And it's not relative. You assign a number to it. It's kind of like you might say, oh, it's hotter in Arizona than it is in California today. Okay, that's fine. How much hotter? Well, then you need to know the temperature. Hypotonic tells you there's more water than hypertonic. Water potential gives you a number, so you get a little bit more information that way. So just think of water potential as another way to measure the concentration of water. So hypotonic, that's an O. Hypotonic means you have a higher water potential because hypotonic solutions have more water. Hypertonic have a lower water potential because you have less water. And water moves from hypo to hypertonic solutions. Just like up here, water moves from hypotonic to hypertonic solutions. And then sometimes I tell the kids about a memorable lab we did in biology when I was in high school that we wouldn't be allowed to do today, where you lance your finger and you put a drop of your blood on a microscope slide, and then you wick some distilled water through it and you put it under a microscope and you see your blood vessels swell. Um, the distilled water would be the hypotonic solution. Your blood cells would be the hypertonic solution. The distilled water has a higher water potential compared to your blood cells, which have a lower water potential. So water rushes into those blood cells and they swell and they can eventually lyse. All right. So water potential, let's get a little bit more into the math here. Water potential depends on two things. It has a component that's due to pressure and a component that's due to the amount of solute. Now, fortunately, most of the time we can ignore the pressure potential. That's because in most biological systems, the pressure potential is zero unless you're in a vacuum or if you're placed under physical pressure, if something's pressing down on you. So most of the time we can just ignore the pressure potential. And water potential is equivalent to the solute potential. By the way, a good demo you can do, a straw. When you drink a drink through a straw, you are using negative water potential because you are creating a vacuum in the straw when you suck out the air, and water moves from higher potential in the cup to the lower potential in the straw. And you can talk to kids about, look, have you ever had a straw and it's got a crack in it? Does it work as well? And that's because the air can rush in and you're not able to make the vacuum. Many of your students may have experience with super soaker guns. Super soaker guns use positive water potential because you have to pump them up before you squirt the water out. You're building up that pressure potential, which allows it to be a lot more fun. Okay, so since we're going to assign a number to water potential, we need a reference point. And scientists have decided that pure distilled water, I guess that's redundant, pure distilled water, but you know what I mean. Pure distilled water has a solute potential of 0. That's our reference point. So what that means is that as soon as you add even just 1 molecule of solute to that water, the water is going to become less concentrated and the solute potential becomes negative. Okay, how negative? Well, that's what this equation is for. Kids do not need to memorize this equation. It's on the formula sheet. They don't need to memorize what these things stand for, but I think it's good for them to know. Solute potential is minus I CRT, okay? I stands for ionization constant. How many ions does the solute form in solution? If it is a covalent compound, like what we're using in this lab, sugar does not form ions, it doesn't separate, so its ionization constant is going to be 1. However, if we're using something like sodium chloride that does ionize into sodium and chlorine ions, then I would equal 2, okay? C is the concentration of solute. R is a constant, 0.0831 liter bars per mole Kelvin. And T is temperature, and you need to use temperature in Kelvin for 2 reasons. One, because you want the units to cancel out in your constant for R, which also has Kelvin. And 2, Kelvin is an absolute temperature scale. You have no negative numbers. And to get Kelvin, if you're not familiar, it's just degrees Celsius plus 273, and that gives you Kelvin. So let's look at a couple of quick calculations here. Make that a little bit bigger. Okay, one of the solutions we're using in today's lab is a 2 molar sucrose solution, and we're going to assume room temperature is 21 degrees Celsius, which if you add 273, it adds up to 294. Okay, so solute potential is going to be minus 1 Y1, because sucrose doesn't ionize, times the concentration, which is 0.2 moles per liter, times our R constant, 0.0831 liter bars per mole Kelvin, times 294 K. Now let's go through and cancel our units. Kelvin cancels out, moles cancel out, liters cancel out, and you're left with bars, which is the unit we usually use in AP Bio for water potential. If you pop this in your calculator, -1 times 0.2 times 0.0831 times 294, you get a water potential of a 0.2 molar sucrose solution is minus 4.89 bars. Now, let's compare that to a more concentrated sugar solution, a 0.8 molar sucrose solution at the same temperature. So everything's going to be the same except for the concentration, right? It's still sucrose, so I is still 1. Same R, it's at the same temperature. And when you crank this out in the calculator, it's minus 19.55 bars. Now, minus 4.9 is bigger than minus 19.55, right? So water is going to move from the higher water potential to the lower water potential. Water would want to move out of the 0.2 molar solution and into the 0.8 molar solution. So that's how water potential works, and that's kind of how I present it to my students, except with my students, I'd probably go a lot slower than I just did with you. Have a great evening. Bye.